All right, hello class. Today's lesson is on complex numbers. This will be our first topic in Chapter 4. And Chapter 4 is solely dedicated to quadratic equations. And we'll talk about what that means here in a little bit. But again, today's specific objective is on complex numbers. And also the solving by taking the square root. So both of those things will come up, and here's the more detailed parts of the objective. All right, so the first thing I want to notice, again, 4.5 in the book, and let's talk a little bit, what are quadratic equations? Quadratic equations are any equation where you have an x squared, and the square is the key part, okay? Lines always have x to the first power, y equals mx plus b. There's no exponents, but once you have a square power, it makes it a quadratic, and it's a special family. If it's a cube power, different family, not a quadratic. Quadratics is the moment it has that. So even if I had x squared, and then I said, plus 2, that's still a quadratic equation because it has an x squared, even though it has other stuff with it. So let's go ahead and keep that in mind. All right, so how to do these problems, okay? Basically, you have to get x by itself. So first problem here, simply divide by 3, and we get x squared is equal to 7. And then we say, all right, how do we get rid of the square term? Well, what undoes something that's square? Taking the square root. So we take the square root of this side here and this side over here. And the square root and the square root cancel each other, and you're left with x all by itself. That's saying what number times itself, and you're undoing that. So you're left with x. So e equals the square root of 7. Now, the other thing that we have to add to this is a plus minus. Because since we're solving, you think, what numbers work? Well, if we take the negative square root of 7 and square it, well, a negative times a negative cancels out. The square root times the square root cancel each other out, and you're left with this 7. So plus and minus is always going to happen when you're solving and taking the square root. All right, let's look at problem number 2. Again, this linear algebra. How do we get rid of this? Well, the first thing you have to do is get the x squared by itself. So I'm going to multiply by the reciprocal, both sides. Cancel, cancel. We have x squared is equal to, and again, I'll reduce. That's 18 divided by 2, which is the same thing as 9. Okay. We say, all right, now how do we take the square root of this? Once again, take the square root. And again, a lot of times it would probably be beneficial. Let's go ahead and put the plus minus in right away so we don't forget. But obviously the square root and the square root cancel each other out, and you're left with x equals plus or minus 3. Because just think, if you put 3 back into the equation, it works out. And if you put negative 3 into the equation, it still works out. So both plus and minus work. So when you're solving quadratics, most likely you can get 2 answers. So that's the important thing to know there. Now, what's new for this topic is the fact that no matter what quadratic you have, you will always have an answer, and most likely 2. But not all answers are real. So here we have this slide. You're probably looking and say, what is going on here? Well, here we have a horse, and here we have a unicorn. So I ask you, do unicorns exist? Well, math will prove that they do exist. They're called imaginary numbers, just like unicorns are imaginary animals, but they do exist. You just can't see them. You can't comprehend them. You can't visualize them. But evidence shows that they are still in existence. We just can't see them in the real world. So we're going to kind of come back to that metaphor as we move on. So what is an imaginary number? Well, let's try to solve this problem right here. X squared plus 1 equals 0. Well, algebra tells us subtract 1. We have x squared is equal to negative 1. And now if we take the square root of both sides, we have x equals, now the square root of negative 1. Now if you plug this into your calculator, you get an error, because it's not a real number. No number times itself will ever equal a negative number. So we have a special definition for this, and it's called I. And it represents all imaginary numbers, all unicorns. And they're numbers that do exist. We just can't physically comprehend it or use it in the real world. But the good thing about imaginary numbers are the solutions, when you look through them, when the problems that involve imaginary numbers, when you look through them, a lot of times produce real answers. And we'll see that as we move on. So we have a special name for this. So x is equal to, not the square root of 1, but we call this just simply lowercase I. And I is the square root of negative 1. So if I simplify this, and the one thing you want to pick up from this lesson is that I is equivalent to the square root of negative 1. Anytime you see that negative on the inside of a radical, so I'm going to highlight it here in blue, that's telling you I, and it's the definition of imaginary numbers. And how do you have the square root of 1? Well, that's the kind of purpose here. So this is not a question where, I don't understand it, I can't visualize it, doesn't make sense, because it's imaginary. But you have to trust that it does exist, and these problems, as we work through it today, will show you they do produce real answers. So we have to learn how to work with this I. All right, so over here we have, let's leave them over here. I, so what's I? The square root of negative 1. Well, what's I squared? Well, that's simply I times I, which is the square root of negative 1 times the square root of negative 1. So if we multiply these two together, what do we get? And I'm just going to write the answers, I guess, over on this side, because I kind of ran out of room here. Well, square root times the square root, they cancel each other out, and you're left with what's on the inside. So if you take I and you square it, you get negative 1, which makes sense. If you took the square root of something squared, you get I. So what's I cubed mean? Well, we know that I squared is negative 1. But then we have another I. So there's a total of 3 i's, I to the first power. So negative 1 times I is what? Negative I. So that makes sense there. I to the fourth, well, that could be broken down two ways. I squared times I squared. When we just learned that I squared is negative 1, so what's negative 1 times negative 1? Simply 1. So the items that we're going to pick out here is that I is equal to the square root of negative 1. I squared is equal to negative 1. I cubed is negative I. And I to the fourth is 1. All I problems, imaginary problems, is one of these four answers. It's either a real number, negative 1 or 1, or it's imaginary, square root of negative 1, which is I, or negative I. So notice, like in this example right here, here's proof that we could take an imaginary number and square a number that supposedly doesn't exist, and all of a sudden it turns into a real number, negative 1. So this is perfect evidence to show that these numbers do exist. It yields a real number, which is negative 1. So since we get back to 1 every time we have 4 imaginary numbers, every group of 4 of imaginary numbers will yield the product of 1, which is nice because 1 times anything always equals itself. So we're going to use that principle in these next couple problems. So again, up here in the corner, we have my little cheat sheet to remind us what all those different items are. I to the fifth power. Well, I'm going to group it into groups of 4. So I to the fourth, how many of those do we have? Well, we have one group of them, and we have an I left over. And we just learned what's I to the fourth power? Well, that is the same thing as positive 1. And positive 1 times I is simply I. So that's how that works. So you're basically taking every group of 4 out, they cancel each other out, and you're just looking at the remainder, what's left after groups of 4. Let's look at I to the 10th. Well, here we have I to the fourth power, which is 1, and how many of those we have? We have 2 of them. 4 times 2 is 8. So there involves 8 i's. What's our remainder? I squared. So looking over here, all I did was break it into groups of 4 and see what I have left over. So I to the fourth, that's 1 squared, which obviously is just 1. I squared is negative 1. And then 1 times negative 1 is simply just negative 1. So I to the 10th is simply negative 1. So that's how we want to break that down. Put them in groups of 4, look at the remainder, and then simplify. And most of our answers are going to end up in one of those 4 formats. All right, let's take a look here at the bottom 2. Here we have I to the 52th power. So we have to look, how many times do we have groups of 4 going to 52? Well, I to the fourth power, that's 13 times. So what's 1 to the 13th power? Well, that's easy, 1. So if I took I and multiplied it 52 times, you would end up with 1. Okay, so it's a constant repeating pattern. Every 4, it starts over at 1 again. 143, so again, I'm going to look, how many times does 4 go into 143? So I'm going to start with I to the fourth power. 4 goes into 143, let's see, 3 times, and then 23, so we have 5 times with I, 3 left over. I'm just going to check my math real quick. It is Friday, so we have 35 times 4, is 140 with a remainder of 3. That looks pretty good. So we have 1 raised to the 35th power, which obviously is just 1. And I cubed, we're looking up here again, is negative I. So what's 1 times negative I? Guess what? Negative I. So our answer for I to the 143rd power is negative I. So how can you simplify imaginary numbers? That's one way. Simplify to one of these 4 elements up in the upper right-hand corner. All right, now, how do we apply this to other numbers that involve more than just the I? Well, here we have the square root of negative 6. This could be broken down to the square root of negative 1 times the square root of 6. Okay? And being that they're both square roots of each other, we can combine them. So what is the square root of negative 1? That's simply I, and this is simply the square root of 6. That doesn't change. All we're really doing is taking that negative out, isolating it, and it turns into I. Now, this is this proper format now. Being that we have an I and a radical together, it is proper to show the I before the radical. Because sometimes students will write it like this, and it's confusing on if the I is inside the radical or outside, so we don't want to do that. We want to show it this way over here. So I'm going to put a star by that. So what is the square root of negative 4? Well, that's negative 1 square root times the square root of 4, which we all know to be 2. And that's I. Now, proper format when we don't have the radical is you put the number first, put the I after it, just like you would almost a variable, but this is the variable, we know what it is, it's the square root of negative 1. And that's how you'd write your answer. Okay, so 2I. So notice, number by itself, nice and clean, you put the I in the back. If we have a radical, just to save from confusion, we put the I in front. Okay, let's look at the bottom 2 problems down here. So again, to solve for x squared, we take the square root, both sides, plus and minus. X is by itself, and we have plus or minus the square root of negative 3. We see the negative on the outside, so I'm going to make it an I. Square root of 3 doesn't change, and we have plus and minus. So x is equal to plus and minus I radical 3. Notice 2 answers here. Okay, that's the plus and the minus. Look at number 6. First step, subtract the 11. We have 2x squared equals negative 48. Divide by 2, obviously. X squared is equal to negative 24. Take the square root of both sides. And x is equal to plus or minus the square root of negative 24. Now, here, we have to rationalize the radical here. So I'm going to take 24 and break it down. So we have x is equal to plus or minus. I'm going to take the I out right away. And 24 breaks down to the square root of 4 times the square root of 6. We know the square root of 4 gets simplified to a 2. So x equals plus or minus 2. Now notice, I have the number. Proper form says I'm going to put the I after it, and then I'm going to follow it up with the square root of 6. So my final answer should look like that. Square root of 4 becomes 2. I stays the same. Square root of 6 stays the same. Plus and minus in front. So we have 2 answers here, and that is the solution to that equation right there. Okay. So those are 4 good examples to kind of show you how these apply to regular algebra problems. And yes, this is an answer. It just happens to be imaginary. So here we have 4 unicorn answers. Okay, complex numbers. This is how we work with imaginary numbers because we see now, I squared all becomes negative 1. So it's the same type of number, but now we're going back and forth between real and imaginary. So how do we handle that? We call this complex numbers. And complex numbers always follow this form, a plus bi. You put the real number first plus bi, which represents the imaginary, hence the I. And a and b are just coefficients, just numbers. Altogether, a plus bi represents a complex number. So the whole thing is really imaginary because the I is involved, but we represent it with a real number and imaginary put together. We call it a complex number. It's very similar to like terms. So let's look at number 7. How do we tackle this complex number plus this complex number? So they're both imaginary because they're complex, and we're just going to put them together. So we say, all right, what is the same here? Well, if I look at 3 and I look at 2, they're similar. So I can say 3 plus 2 is 5. And then we look at negative I plus 3i, well, that's negative 1 plus 3 is 2i. And there's my final answer. And notice we have the a in front, and then we have the bi in the back. I'm going to put the a here in green so it matches. So right here is a complex answer to that problem. Simplified. Let's take a look at the next one here. I'm going to isolate all my real numbers first. So here, here, and here. Notice I'm going to distribute that negative, so that becomes positive. So we have positive 2 minus 3i. Distribute the negative on the back side, so we have positive 10, positive 4i. And the 3 just comes down by itself. So 3 plus 2 plus 10 more, we have 15. And then we have to look at the I, so we have negative 3i plus 4i for this positive 1i. Notice a, which is the 15, plus bi. B in this case is 1, and we have the same form, okay? A plus bi form. So handling complex numbers is similar to combining like terms. Okay, let's look at these problems here. How do we multiply using complex numbers? Same thing. I is similar to a variable. So this is a variable that we know what the answer is, which is square root of negative 1. So we simply distribute here. So here we have negative 3, and I times I is I squared. But what we have to do here is we have to say, hey, can we simplify that? Sure we can. I squared we learned to be negative 1. And what's negative 3 times negative 1? Positive 3. So here's another good example. We start with an imaginary problem, and we end up with a real solution. And this is another example of how imaginary numbers work in our existence with working with math. Here we have, similar to like a FOIL problem, for those that understand what that is, but it's basically a double distribution. I'm going to take the 2 and multiply it here and here. So we have 8 plus 6i. Okay, so 2 times 4 is 8, and then 2 times 3, obviously 6, and you just put the I in there, similar to a variable. Then we're going to do with the I here, so that's going to go to the first term, second term. So we're going to have negative 4i, and then we have negative 3i squared. So negative I times 3i is negative 3i squared. But again, we need to take that negative 3i squared and convert that to negative 1. So I'm just going to rewrite the whole problem and say, okay, what do we have here? Well, negative 3 times negative 1 is positive 3. And I'm just going to go through all the steps so we don't lose anything here. Say, okay, let's combine like terms. That should be a positive there. And we say, all right, 8 plus 3 is 11. 6 minus 4 is positive 2i. You know you are done when you're in a plus bi form, where everything's simplified with real numbers followed by imaginary numbers for a complex solution. All right, let's look at this last one here. So here we have, again, I'm going to go ahead and you could do one of two things. FOIL first and then distribute the I, or you can distribute the I first and then FOIL. I'm going to do that because a lot of students get tricked on this one. So I'm going to take the I and multiply it. Now, again, you don't have to multiply it to the other term too. You just have to do it once. I'll do off to the side here. What's another example of that? If you have 2 times 4 times 6, well, you just go 2 times 4, which is 8, times 6, which is 48. You don't go 2 times 4, which is 8, and then go 2 times 6. That doesn't make sense. So we only do it once. And I'm going to do that problem like this so students can see the proper way to do this problem. I times 2 is 2i. I times I is negative 1 with a negative in front, so I'm going to change that to positive 1. So that first part distributed looks like that. Followed by 4 plus 3i. Okay, I'm just going to go through the thing and follow again the double distribution. So I'm going to have 8i first, and then I'm going to have 6i squared, and then I have 1 times 4 is 4, and then 1 plus 3i is 3i. I noticed the I squared here, so I'm going to change that to a negative 1 times 6, which is negative 6. So now I have reduced all of my imaginary elements, and now I'm going to combine my a's and my b's. So we have negative 6 plus 4 is negative 2. Put the a first. 8i plus 3i is 11i. Again, a plus bi form. So those are the simplified versions of those problems. Notice they all look similar in the fact that this. So even the 3 up here, what is the bi? Well, it's just 0 i's. We don't show them because they're not existent in that problem. All right, How do we divide using imaginary numbers? Well, here, it's almost like radicals. You can't have a problem that looks like this. 4 divided by the square root of 3. We all know, well, you can't have a radical in the bottom. It's improper, so we need to rationalize it. So what we do here is just multiply by the square root of 3, top and bottom, and you have 4 radical 3 divided by 3, and this looks like a proper answer. Even though it's the same number, it's now proper. The same thing with imaginary. We cannot have an I on the denominator of a fraction, so we have to get rid of it. So just like rationalizing, we want to multiply by that I. So if we multiply the bottom by I and the top by I, we can simplify this. So the top is going to be I times negative 3 is negative 3I. And in negative 5I times I is negative 5 times I squared. On the bottom, we have 2I squared, because I and I make I squared. Well, we all know that I squared is going to be negative 1. So I'm just going to simplify this. Negative 3I on top. The I squared is negative 1. Negative 1 times negative 5 is positive 5. On the bottom, we have 2 times negative 1, which is going to be negative 2. This is now a proper answer. Notice it's still complex because we have an I involved. Now, again, I'm probably going to rewrite this so I have an A plus BI form. So my final answer should really look like this. 5 minus 3I. Notice the 5's first. And again, negative 2 on the bottom. And again, this is this proper notation. All right. Number 13 here. This is called a conjugate. Okay. So remember that word conjugate. And it's a way to get rid of the I in the bottom. And what a conjugate is, it's the exact same thing, but instead of a minus, I put a positive. So I'm going to multiply the bottom by 2 plus I. And notice, I'm going to do it on the top as well, because that's what math tells us to do. Notice it's the exact same expression. We have a negative and a positive. So now if I multiply the bottom here, watch what happens. 2 times 2 is 4. 2I, and then we have this negative I times 2 is negative 2I. So there's my middle term. I times I is negative 1. Then we have a negative there, so I'll just show that. Negative I squared. Now let's go ahead and simplify this. We know that this I squared here in the end is really negative 1. So a negative times a negative is positive positive. 4 plus 1 is 5. And then notice 2I minus 2I, those cancel each other out, and you have 5 on the bottom. So that's a good way to clean up the bottom by multiplying the conjugate, because notice the i's disappear. So I'm going to put that on the bottom. 5 goes down there. Then on the top, you just go ahead and distribute. 5i there, 5i there, and we have, again, I'm going to put the i's in the back, so the 10i is going to go in the back. And then notice 5i times I is 5i squared, which we know to be negative 1. Negative 1 times 5 is negative 5. So here's the proper answer to that problem. Notice both solutions have a real number on the bottom and then the imaginary on top, complex. These are just proper ways to write these numbers. So we've seen how do you simplify I, how do you add it, multiply it, divide it. Again, this whole lesson is on how to work with complex numbers and basic operations. So again, looking at our objectives, you can kind of go through there to kind of see where you're at, working with complex numbers. For homework this week, and I want you to try a couple of problems. I highlighted them here in yellow. So for the weekend, for the next class period, come to class, I want you to attempt number 7, number 11, number 16, 23, and 29. So 5 problems, but again, they're shorter problems, and that way we can take a look to see how you're doing, and then obviously in the following class, we'll work on a little bit more complex problems as well. Have a good evening, and we'll see you next class period.